This morning she's going to talk about contaminants. Um, I think safe to say, Sherry, urban related contaminants. I think that's what was in your abstract, and included in that things like PFAS and contaminants of emerging concern. So with that, I'm going to give it off to you, Sherry, and you can take it from here.
Thank you, Mark, for that nice introduction. And as Mark said, I'm going to be speaking about the urban contaminants that we've been monitoring in the state's groundwater. Let's see if I can get to the, okay. And from 2 weeks ago, you remember that Rebecca Higgins gave us a great presentation on PFAS being transported in the East Metro through the Project 1007 stormwater system. And today, I'm going to be stepping you back to the statewide scale and discussing contamination found in the state's ambient groundwater. And I'm going to be focusing mainly on contamination in the groundwater that underlies urban parts of the state. And this slide shows the roadmap of today's presentation. I'm going to start with just describing some basic information about groundwater in general and the state of Minnesota's groundwater, just to get everybody up to speed on the terms that I'm going to be using in the remainder of the presentation. Then I'm going to be speaking about the state's approach to groundwater monitoring, and specifically about the MPCA's role in groundwater monitoring. And then I'm going to give an overview of our ambient groundwater monitoring network. And then I'm going to discuss some of the results that we've been finding on urban contamination in the groundwater. And specifically, I'm going to talk about chloride, volatile organic compounds, or VOCs, and these are chemicals that are found in gasoline or solvents. Then I'm going to talk about contaminants of emerging concern, or CECs, and these chemicals are prescription and non-prescription medications, insect repellents, and other household chemicals. And then finally, I'm going to end with describing some of our PFAS monitoring results. And PFAS, again, as most of you know, are the fluorinated chemicals that are used in nonstick cookware and many, many other products. And first, I just want to talk about, just give you some basic information about the groundwater. And most of you know that Minnesota is the land of 10,000 lakes, and we see rivers and streams everywhere. But really, our biggest freshwater resource is our groundwater. And this is a graphic that I took from a researcher at Penn State University that shows the distribution of water throughout the whole planet. And the green bar here just shows all of the Earth's water. And as most of you know, most of the water is salt water, with only about 3% being fresh. And of that fresh water, you know, almost 70% of the Earth's fresh water is stuck in glaciers and ice caps. And the remaining fresh water is stored in our groundwater system. And so even though we're the land of 10,000 lakes, this little blip of a bar shows that, you know, under 0.5% of the Earth's water is actually stored in streams and lakes. And in Minnesota itself, groundwater is a very important water resource, and this supplies 3/4 of the state's drinking water and 90% of the water that we use to grow our crops. And many times you might hear that groundwater being called underground lakes, and you might see some visual image of the groundwater like shown in this scene from the Lord of the Rings, where people are walking underneath the earth in these fantastic little caverns and stairways, and then they just encounter these beautiful blue lakes underground, and this really is just fantasy. Most of our groundwater in the state is stored in sand and gravel deposits or fractures in bedrock that underlies those sand and gravels. And this graphic here just gives a boring image of where our groundwater really is. And slide A here shows an enlarged view of the sand grains, and the water is the blue beneath these sand grains would be the groundwater that's extracted from the ground. And sand and gravel deposits are one of our main sources of groundwater in Minnesota. And these deposits can extend to up to 400 feet thick in some parts of central Minnesota. And the remaining groundwater, as I said, is stored in fractures in rock, like is what's shown here in image B, which just depicts some fractures in granite, which mainly would be a source of groundwater in northeastern Minnesota and parts of southeastern Minnesota. And the image here in box C just shows the fractures that occur in limestones, which are a great source of groundwater throughout the state of Minnesota. And limestones are a rock that can be easily dissolved by rainwater, which naturally has a slightly negative pH. And in limestone, the fractures are dissolved by solution to form these conduits and caverns. But and again, like I said, these caverns and fractures, they're not very big and they aren't large enough to fit a person. And this next slide just shows a cross section of what the groundwater looks like. And there's a couple of key points that I want to point out here. This dashed line is called the water table. And this is where the groundwater begins. And anything below the water table is called the saturated zone. And within the saturated zone, all of the sand particles have water in them. Or if the saturated zone is comprised of bedrock, all of those fractures or caverns in the bedrock are fully saturated with water. And above the water table is called the unsaturated zone, or sometimes it's called the vadose zone. And in this part, all of the sand particles or crevices in the rocks are not completely filled with water. And another key point I want to point out on this slide is you can see that the groundwater is connected to the surface water body. And in many parts of the state, the groundwater flows naturally to our streams and lakes. And it's because of this groundwater inflow that our streams don't dry up during times of year when we haven't gotten any rain. And one last thing I want to point out on this slide is this graphic just shows the water table as this stagnant line. And this isn't the case. I mean, the water table rises and falls in response to how much rainfall we get. And also, if we had put a well in at this point and pumped it, we would also change the level of the water table also. And this next slide again shows another cross section of the groundwater. And in this case, we have the water table, but then we have a couple of different aquifers. We have the unconfined aquifer near the surface, and then we have a confined aquifer below that. And key point I wanted to point out here about our groundwater system is that it's not just one groundwater, but there's many different aquifers that underlie our land surface that contain groundwater. And these aquifers are separated by what's called a confining bed. And these confining beds are made of materials that don't allow water to flow readily through it, like clays or shales. And another point that I want to make on this slide is that how quickly water gets to these confined aquifers depends on the geology. at a place, on this land surface near the tree, any water that would rain down on the land surface would first have to flow through the unsaturated zone, then through this unconfined aquifer, make its way through the confining bed, and then reach this aquifer shown in white. But if we were at the point of this aquifer where the arrows are here, the rainwater would flow right away into this confined aquifer. And if there was any contamination on the land surface, it would be transported to the confined aquifer right away there as well. And one other thing I wanted to mention about this slide is you might have heard the term artesian water. Usually this would be in commercials for beverages. And what the term artesian refers to is that this confined aquifer is under pressure. And if you pop a well into this confined aquifer, the water level flows upward above the level of the confined aquifer, which is shown by the white. And in the case where the well in the confined aquifer flows above the land surface, that would be referred to as a flowing artesian well. And a well like this you wouldn't even need a pump to get water out of it. This picture here just shows a photo from about 100 years ago of a flowing well in South Dakota, which actually water shot up about 100 feet from the land surface. And this next slide shows two graphics that I took from publications produced by the Minnesota Geological Survey. And I wanted to show you this to just illustrate how many different bedrock aquifers underlie the land surface in southeastern Minnesota. Each of these little boxes here show a different geologic unit, and many of these are aquifers and contain water. And as you can see, there's just a whole layer cake of bedrock aquifers in southeastern Minnesota, which is one part of the state where there's just vast amounts of groundwater. And if you went to this yellow part in Mower County and drilled a well deep enough, you would encounter all of these geologic units. But as you radiate outward, you encounter fewer and fewer of them. And in the Twin Cities metropolitan area, our bedrock aquifers primarily start with the St. Peter and go downward. And two aquifers that are very important sources of water supply in southeastern Minnesota and the Twin Cities are the Prairie du Chien and the Jordan. And you're going to hear me talk a bit about them in the remainder of this presentation. And next, I want to just describe our statewide approach to groundwater monitoring. And in Minnesota, 4 different state agencies are charged with monitoring the state's groundwater. That would be the Health Department, the MPCA, the Department of Agriculture, and the DNR. And this multi-agency approach was specified in the Minnesota Groundwater Protection Act, which was enacted in 1989. And this act specifically directs the MPCA to monitor for contamination from non-agricultural sources. And this next slide just shows the different agencies' roles in groundwater monitoring in Minnesota. And the Health Department is charged under the Groundwater Protection Act to monitor the state's public drinking water supplies. They also are in charge of our state well construction code. And the Health Department also is responsible for determining the health risks associated with any chemicals that are found in the state's groundwater. And as I said before, the MPCA's role in groundwater monitoring is to look for non-agricultural contamination. And so we're responsible for monitoring for chemical releases of industrial pollutants or chemicals from consumer products. And And we also do ambient groundwater monitoring just to see what the impact is of routine chemical use on groundwater quality. And the Minnesota Department of Agriculture, they're responsible for monitoring the state's groundwater for pesticides. And they're also responsible for the state's pesticide management plan. And finally, our neighbors at the DNR are responsible for monitoring how much groundwater is available. And they also work with the Minnesota Geological Survey to produce groundwater atlases, which show how vulnerable our state's groundwater is to contamination from the land surface. And this next slide just shows our part of our agency's strategic plan, and I just brought this up to also point out that preventing and reducing pollution to our groundwater is part of our agency's strategic plan. And another related effort is to manage places that we know are contaminated to reduce the risks to human health and also, reuse that land. And this next slide shows a map of purple dots across the state where our agency has assessed pollution from petroleum remediation sites or solid waste sites. And I just bring this up briefly just to point out that my talk today is not going to center on these places where we know contamination exists, because this monitoring is done by a lot of people in the agency. But instead, I'm going to focus on the chemicals that we find in the ambient groundwater. And when I say ambient, these are the places in the groundwater system that aren't next to those known point sources of contamination, which could be spills or accidental leaks. But the contamination that we are finding in this monitoring is primarily just due to the normal routine use of chemicals. And the map on this slide shows our current ambient groundwater monitoring network. And this network was started in 2004 and currently consists of about 270 wells, which are shown by the gray dots on this map. And I've also overlain on this map map that was put together by the DNR showing the pollution sensitivity of the near surface materials. And the tan areas on this map show parts of the state where the groundwater has a low to ultra low vulnerability to contamination. The orangish or rosish areas on the map show parts of the state where the groundwater has moderate to high vulnerability to contamination, or the bedrock here is just karstic and just has a lot of caverns and right near the land surface. And the dark tan color just show other areas, which in the northeastern part of the state is where there's crystalline bedrock right near the land surface, or in north central Minnesota where there's just vast peatlands. And I overlaid my network with this map just to point out that our network is specifically designed to look at groundwater that has a moderate to high vulnerability to contamination. And we did this on purpose because we want to see what chemicals can make their way to the groundwater before they break down. And also we want to, with our monitoring, track trends in groundwater quality. And so we deliberately wanted to choose groundwaters that were fairly young. When you get into these parts of the state that have low to ultra low groundwater vulnerability, if you do the work to age date that groundwater, you may find that it's hundreds to thousands of years old, and sampling those wells over time, just, we wouldn't have enough information to say how it's changing. And I also wanted to point out with this map that you can see that our network isn't evenly spread across the state, but it focuses on urban areas like the Twin Cities metropolitan area, St. Cloud, Brainerd, and we also did that deliberately to meet our charge of assessing non-agricultural contamination. Our sister state agency, the Minnesota Department of Ag, also has an ambient groundwater monitoring network that focuses on the ag areas of the state. And if I would overlay our network with theirs, you'd see that it gives a fairly complete picture of groundwater conditions across the state. And I also wanted to point out that in our network, we do monitor some bedrock aquifers in southeastern Minnesota, and these primarily are domestic drinking water wells that we sample. And the bulk of our network focuses on the superficial sand and gravel aquifers, which are located throughout the state, but are mainly concentrated in the central part of Minnesota. And for our superficial sand and gravel aquifer monitoring, we take into account both the land use and the type of materials that make up these aquifers when designing our network. And we took into account the composition of the superficial sand and gravel aquifer networks because these really vary across the state depending upon the glacier that deposited them and where it came from. Their sand and gravel aquifers were deposited by a series of glacial advances that occurred anywhere from 2 million to about 12,000 years ago. And some of these glaciers came from the northeast, and these glaciers traversed rocks that would be red sandstones in the Lake Superior basins, or basalts, and these left deposits that were really silicious in composition and have a brownish to reddish color. And the glacier advances that came from the northwest, these traversed limestones, and some of these limestones also had shales in with them, and these left deposits that were calcareous in composition and also had that shale. And so if we here's another map just showing the characteristics of our sand and gravel deposits mainly in northeastern Minnesota. These would be more silicious, and in the remainder of the state would be calcareous. And this can make a difference because we measure some contaminants like cadmium that have both natural and human-caused sources. And this is a map that was put together by our state's geological survey. And you can see here for cadmium, the bigger dots show places where the sediments naturally have higher concentrations. And naturally in Minnesota, there's higher cadmium concentrations in the sediments in western and southwestern Minnesota because these are areas where the sediments naturally contain shale, which is a source of cadmium. And also in our network, as I said before, we deliberately structured it around to monitor different urban land use settings. And we specifically placed our wells in 3 types of urban settings: commercial industrial areas. And when we selected or installed wells for our monitoring network, we deliberately didn't place them next to known point sources of contamination like a Superfund site or a gas station or a dry cleaners. And we also monitor wells in residential areas, including residential areas that use centralized wastewater treatment systems and sewers or wastewater treatment and disposal, and also residential areas that rely on subsurface sewage treatment systems for their wastewater disposal. And for a baseline for comparison, we also monitor a network of wells in undeveloped areas. And these are mainly forested areas in northern Minnesota. And many of these sites are pretty remote. They're actually off of a little dirt path off of the main dirt road in the state forest. And here's just a block diagram showing the network structure for our superficial sand and gravel monitoring. And as I pointed out, We've separated the network based on the composition of the aquifers, whether it's calcareous or siliceous, and then we monitor about 25 wells in each of the different land use settings. And when we initially put this network together in 2004, we used whatever existing wells were available. But with the availability of the funding from the Clean Water Legacy Act starting in 2010, we were able to install over 100 new monitoring wells to our network. And most of this well installation was done between 2010 and 2015. And in this slide, you can see one of our colleagues from the DNR installing a new well to our network. And each year, MPCA staff goes out to each of our well sites and pumps up water using a submersible pump and collects field measurements using this sonde, which is located in a flow-through chamber here. And after that, we pull water samples for analysis of over 100 chemicals and this analysis is either done by our at the Environmental Health Laboratory at Minnesota Department of Health, or we analyze some of the more exotic organic compounds like PFAS in medicines using SGS Access Laboratory in Canada. And as I said before, we routinely analyze for over a suite of 100 different chemicals. And this would include general chemistry like chloride, nitrate, and the other major ions. We routinely look for a suite of about 19 different trace elements, and this would be metals like cadmium, copper, zinc, lead. And we also look for a suite of 68 different volatile organic compounds, and these would be solvents like trichloroethylene or the chemicals that are found in gasoline. And every year we sample about 40 of our network wells for prescription and non-prescription medications. We only do 40 wells each year for this chemical suite just because of the high expense of it. It costs almost as much to analyze one sample for medicines as it does to even drill a well. And periodically, we've sampled our network for PFAS in 2013, and then last year in 2019, we sampled our whole network for these chemicals. And about every 5 years, we put together a report describing the results of our ambient groundwater monitoring network. And the last report that we produced was just published last summer in July of 2019. And first, I want to describe to you some of the chloride results that we've found in our network. And this slide here shows the median chloride concentration in the superficial sand and gravel aquifers and in many of the bedrock aquifers that are present in southeastern Minnesota. And this slide again is based on data from 2013 to 2017. And we can see that the highest chloride concentrations typically occur in the sand and gravel aquifers, which are the uppermost aquifer, and it decreases as we go downward in the layer cake of bedrock aquifers that occur in the state. And a pattern like this, when we find the highest concentrations in the uppermost aquifers, it indicates that one of the main sources is probably pollution from the land surface. And this next slide shows the distribution of chloride concentrations in the superficial sand and gravel aquifers. And the dots on this map indicate the concentration range. The dark blue dots show places where chloride was either not detected or is less than 5 milligrams per liter. And the red dots show the highest concentrations. And these would be those that are above 250 milligrams per liter. And 250 is what's called the secondary maximum contaminant level. And this is a guidance level that's the EPA has for drinking water. And this level isn't put in place because chloride is toxic to humans. It's just that when you get water with more than 250 milligrams per liter, it can have a salty taste that people just don't like to drink. And with this map, you can see that, chloride in the superficial sand and gravel aquifers is just not evenly distributed throughout the groundwater, but it tends to be highest in the Twin Cities metropolitan area. And we've also seen high concentrations in a few other urban wells that we've sampled across the state. And the slide on the right shows chloride concentrations in the Prairie du Chien and Jordan aquifers. And the concentrations measured in the individual wells, again, are coded using the same type of scheme. And you can see that concentrations are typically lower in the Prairie du Chien because it's a deeper aquifer with older water. But I wanted to point out that the green dots with the higher concentrations, they tend to occur in this light purplish area, and that's called the Prairie du Chien Plateau. And in this part of the state, the Prairie du Chien is the first bedrock aquifer, and there's likely higher concentrations here because this is a part of the aquifer where rainwater recharges it. And it can also, with this recharge, this rainwater, any chloride contamination at the land surface can be readily leached into the Prairie du Chien at this point. And this next slide just shows the results of the monitoring in the different urban land use settings that we've done across the state. And again, this is primarily based on MPCA monitoring from 2013 to 2017. And we did work with our sister state agency, the Department of Ag, and they pulled samples from their ambient monitoring network, which is located in ag parts of the state in 2014. And so we do have some data from there for ag areas. And what I wanted to point out with our monitoring is we found the highest concentrations of chloride tend to occur in the shallow groundwater underlying commercial parts of this commercial areas, where the median concentration was almost 82 milligrams per liter. And the next highest median chloride concentrations in the groundwater was the shallow groundwater underlying sewered residential areas, where the median concentration was about 45 milligrams per liter. And as part of our monitoring, we found that median concentrations in ag areas and residential areas using septic systems for wastewater disposal were fairly similar, ranging from 14 to 16 milligrams per liter. And underlying the forested areas of the state, we typically find very low chloride concentrations with a median of about 1 milligram per liter. And we've also found with our monitoring that chloride concentrations, again, they aren't the same in all commercial areas throughout the state. From about 2007 to 2011, we did some monitoring near gas stations. And this was just because when we were initially putting together our monitoring network, there was initially no funding to install monitoring wells. So we just used whatever wells were available, and some of these were upgradient wells that were right near gas stations. And the monitoring we did in these areas showed the median chloride concentration was around 330 milligrams per liter. And this could be because places like gas stations do tend to be located along roads with busier traffic, which might receive more de-icing chemical applications. Or there might even be a greater application of de-icing chemicals just near these facilities just to keep cars and people from slipping during the winter snow and ice season. And another thing that we're doing to measure or get a handle on how chloride changes in these shallow sand and gravel aquifers is to install these little devices here, which are sensors that monitor specific conductance. And specific conductance just measures the electrical conductivity of all the ions in the water, but it can be used to give an indication of how much chloride itself can be changing in the groundwater. And here is one trace of the specific conductance in the groundwater near a well that we've got installed by Square Lake Park in Washington County. As you can see, chloride doesn't remain in conductance, and likely chloride doesn't remain the same in this groundwater, but appears to be highest in March, which is during the spring snowmelt, which can be transporting any de-icing chemicals into the groundwater system. And as I said, we're monitoring about 20 sites across mainly the Twin Cities metro area, just to see how specific conductance is changing. And we do plan to collect some concurrent, do some additional chloride monitoring at these sites throughout the year, just to try to determine some chloride specific conductance relations that we can use. And another task that we're doing as part of our chloride monitoring is we're also collecting bromide samples, because we can use this data to compute a chloride bromide ratio, and this can give us an indication of what the chloride sources are in the groundwater. And we can use a chloride bromide ratio to determine sources, because there's a big difference between the chloride and bromide concentrations in the groundwater naturally. And when you take these ratios, you can get a very large range. And also, one important source of chloride to the groundwater, which is salt, either used as a de-icing chemical or put in water softeners, tends to be deficient in bromide. And that's because when salt is deposited, the salt that's mined from the earth is deposited, it's deficient in bromide, because bromide is just a wee bit more soluble compared to bromide. And so we can use this to see if there's a chloride bromide ratio that's greater than 1,000. This indicates that that water sample was affected by chloride sources from halite, which would be, again, either a de-icing salt or a water softener salt. And in the monitoring that we've done throughout the state, we've found that as you get higher chloride concentrations in the groundwater, it's typically due to an anthropogenic chloride source, either the wastewater, which would be indicated by this orange area shown by intermediate, or by de-icing salt, or water softener salt, which is shown by the reddish area. And in our monitoring in urban settings, we find that 3/4 of the chloride found in the wells in commercial areas, that the source of that would be either de-icing chemical application or water softener salt use. And also, as part of our chloride monitoring work that we've done, we determine trends in chloride concentrations in the wells where we've got enough data to do this analysis. And over the past few years, we've found that chloride concentrations are increasing in about 40% of the wells that we've been able to analyze.
It becomes sodium dominated. So we're starting to see a trend with depth. Nowhere near saline. This is still fairly dilute ground. Next slide.
Is there a question there? But this slide shows that, the red triangles show the wells where we've got upward trends in chloride in the groundwater, and that's about 40% of the wells where we've had enough data to do this work. And I also want to point out that not all of these wells are the shallow wells right near the water table, but many, especially in the eastern Twin Cities metropolitan area, are domestic drinking water wells that can be over 100 feet deep. And next, I want to move on and briefly describe some of our results from our VOC monitoring that we've done. And this is a suite of chemicals that we don't find very frequently in the state's groundwater. This map shows the detection frequency of the chemicals in this suite that we find most often. And as you can see, we find VOCs in less than 2% of the wells that we've sampled. And the most frequently found VOC is chloroform. And chloroform, we believe, is found in the ambient groundwater, not due to some sort of spill, but just it's likely just related to the use of disinfectant public water supplies. And this map shows the places that are marked by the green dots where we've detected chloroform in the groundwater. And the one common feature among all of these wells is they're just located in areas where chlorine is used to disinfect their water. And so what we think is happening is that this disinfected water can be used for purposes like car washing, lawn watering, and it's just making its way back into the ambient groundwater. And this next map shows purple dots where we've detected trichloroethylene or tetrachloroethylene in the groundwater, and these are two solvents. And most of these wells where we've got detections of the solvents, they're shallow monitoring wells that intersect the water table, and they tend to be located in commercial or industrial areas. And these areas, if they're in the older parts of St. Paul, it could be due to just legacy spills of these chemicals, or some of these other detections could be possibly used to current use of these products. And next, I'm going to talk a little bit about the CECs that we're finding in the state's groundwater. And we've analyzed using both SGS Access and the U.S. Geological Survey labs over a couple hundred of different CECs in the state's groundwater. And this bar chart shows the CECs that we've detected most frequently in our 10 years of monitoring for these chemicals. And these chemicals are found a little bit more frequently than VOCs, with sulfamethoxazole being detected, a little over in 12% of the water samples that we've collected. And one thing I wanted to point out is that the chemicals in this class that we find most frequently in the state's groundwater, including the antibiotic sulfamethoxazole, the X-ray contrast agent iopamidol, bisphenol A, and the anti-corrosion agent tolyltriazole. These all tend to be chemicals that are fairly resistant to degradation, and so this would make them persist as they make their way into the groundwater system. And this next map shows the number of CECs that we've detected in any individual well that we've tested between 2009 to 2019. And as you can see, we've slowly cycled through and monitored most of the wells in our network for this suite of contaminants. And the blue dots on this, the dark blue dots on this map show wells where we haven't detected any CECs, and going up to the red dot, which shows the well with the greatest number of detections. And what I wanted to point out with this map is typically when we find these chemicals in the groundwater, we usually find anywhere from about 1 to maybe at the most 10 different chemicals in any one water sample. And we also see that the number of CEC detections in the groundwater also varies with land use. And we do tend to find CECs more frequently in the shallow wells that we've monitored in commercial or industrial settings compared to the other land use settings that we've assessed. And finally, in the last few minutes that we have, I just want to give you a brief overview of some of our PFAS results. And we've periodically sample our network for PFAS in the groundwater. This map shows the bulk of the sites that we've monitored in the sampling that we did last year in 2019. And This is a suite of organic chemicals that we find most frequently in the groundwater. And we detect the PFAS in 60 to 70% of the wells that we've tested. And the chemicals in this suite that we find most frequently are the short chain chemicals like PFBA, whose concentrations are shown in this map. And we find the short chain PFAS more frequently because these are the chemicals in this suite that are most mobile in the groundwater. And this map, just shows the concentration ranges of PFBA that we found last summer. The dark blue dots show places where PFBA was either not detected or less than 10 nanograms per liter. And the orange dots show the highest concentrations in the ambient groundwater, which range anywhere from 190 to 651 nanograms per liter. We did detect in the ambient groundwater a couple of chemicals that many of you are very familiar with, PFOA. We found that in 35% of the wells that we tested. We found PFAS in about 24% of the tested wells. And this table here just shows the detection frequency of the various PFAS that we analyzed for last summer in the ambient groundwater samples. We looked for a total of 33 different PFAS, and the preliminary data that we've got back to date shows that we've found about half of those chemicals, 16 of them. And of this suite of chemicals that we've analyzed in the groundwater, there's only human health guidance for 5 of them. And we have found some samples where PFAS, perfluorohexane sulfonate, and PFOA exceeded the guidance that was put out by the health department. And this map here just shows the places where we did have PFAS health exceedances. And these were all in shallow monitoring wells that intersected the water table. And as you can see that these wells aren't just located in the East Metro area where we know we have regional PFAS contamination, but are also in other primarily, urban settings across the state. And when we look at our PFAS data with respect to land use, we also find that we find PFAS chemicals more frequently in the shallow groundwater underlying urban settings, especially residential areas that use centralized sewer systems in commercial areas, compared to undeveloped parts of the state, which typically only have one PFAS found in the water samples when we do find it. And finally, we don't have a lot of data to determine the trends in PFAS in the ambient groundwater, but there is a few wells that we've sampled multiple times for PFAS. And because many of the wells that we sample are very shallow and right near the water table, which means that this water is very, very young, we've age dated some of it using sensitive techniques like sulfur hexafluoride or tritium helium age dating, and we found some of this water can be months old. So it's not surprising that we can see drastic changes in the numbers and concentrations of PFAS that we've monitored in these wells. And this first graph just shows a bar chart of the various PFAS that were detected in a water sample in this monitoring well in Kroening County, which is just located in a residential area. In 2013, we found all of the 13 PFAS that we monitored for in the water sample. But in subsequent samplings in 2017 and 2019, we only found 4 different PFAS and at much lower concentrations. And similarly, in this monitoring well in Anoka County, which again is in a I believe is in a residential area, we found a really high concentration of perfluorohexane sulfonate in 2013, but subsequent samplings have shown that this concentration has decreased, although we have seen an increase in PFAS in this particular well. And to date, we haven't gone out near our monitoring wells to see what the sources of the PFAS are to them, but it's something we're talking about in our program. And finally, I really thank you for your attention, and I think that we might have a little bit of time for questions. Is that correct, Mark and Brooke?
Yeah, so we have one question already out there from Paul.
Okay.
Are there limitations for which contaminants you can detect?
Yeah, it would depend on, I mean, there's just some things like gold that it's just hard to get down to a laboratory detection limit where we just can't measure that chemical at a concentration that it would be present in the groundwater. Yeah, so there are limitations with the laboratories, and also just with how many chemicals we can find in the groundwater. We're also just limited by our budget because when we get into chemicals like the CECs, we're talking a couple $1,000s per analysis, and so I just have budgetary limitations on what we can do.
If that doesn't answer your question, Paul, you can certainly unmute and ask your question as well.
Yeah, it's probably in a chat box too, which I can.
Yep, and we have another question
to bring up.
I can read them, that's fine. We have another question. Is MDA's groundwater data and analysis as robust as PCA's?
They do a different suite of chemicals. They mainly focus on pesticides.
For lack of a better way of putting it, spend some time getting a common understanding of how the process is going to go forward. We're more than happy. Actually, that is something that we need to do. That's a commitment, and I'll offer it here. Yes, Lisa.
And Margaret, this is Lisa.
Okay, sorry. I think we were getting, somebody unmuted themselves and they are on a different meeting or call. So go ahead, Sherry, your answer to about the difference between MDA's, groundwater monitoring, and PCA's.
Yeah, we don't focus on the same suite of contaminants. The one contaminant that we have that's in common would be nitrate, and that's because there's both fertilizer sources of nitrate and there's other sources like wastewater effluent. But most of MDA's network, to my knowledge, focuses on pesticides.
And then another question, is the decrease of those PFAS concentrations due to the water moving downward to deeper groundwater?
It could be part of it. It could have just been there was usage in somebody's home for those PFAS or an industry that had decreased over time. So we just don't have that small source, or that plume, it could have migrated further away towards a surface water body or downward. We haven't done any investigation to confirm at those exact locations where it's going. We haven't put in a detailed network of wells in those areas.
Okay, another question is regarding CECs. Are we monitoring any wells repeatedly to get an idea of the consistency of the presence and concentrations of these contaminants over time?
Yes, we're starting to do that. One challenge with trying to look for the trends in the CECs is that we've used a couple of different analytical methods over time, and the suites of chemicals, when we switched from federal laboratories to a private lab, the suites of chemicals changed a bit, and over time our reporting limits that the laboratories can achieve are also lowering, so that just makes it a little bit challenging to say how that suite of chemicals is changing in the groundwater, but we are monitoring some of the same wells.
Okay, and another question is, are there plans for expansion of the network or changes to frequency of sampling or parameters? What more would you like to do?
One change that we're hoping to do this summer and next summer is to install some deeper bedrock wells into our network. And we're working with the Federal National Groundwater Monitoring Network to collaborate on installing about maybe 5 new bedrock wells in urban areas in southeastern Minnesota. And we're also planning to do some additional chloride monitoring at a couple of our sites where we've got the conductance sensors, so we can evaluate how much we can use specific conductance as a surrogate for chloride, because one of the big costs of getting out and doing repeated sampling is just the labor of having a staff person out there just to drive to each of those wells to collect the samples. And so as a cost-effective measure, we'd really like to try to use more sensors like the conductivity ones that we have in place.
And then just that follow-up question is, if you were able to expand your monitoring, what would you like to do? What additional wells or parameters would you include in a monitoring program if you had no budget constraints?
I have no budget constraints. I would probably just put in more wells to just get a better handle on the distribution of the suite of chemicals that we're measuring right now. Because we know even in urban areas for chloride, there's a big variation in the concentrations that we've measured. And just to see if we can get some better data to just pinpoint, where those high values are. And also to do some monitoring adjacent to some surface water bodies in urban areas just to see how the chloride could be migrating, to our lakes and streams.
That's great. We have another question. How do you decide what suite of chemicals to test for?
Yeah, we were deciding what suites of chemicals, primarily based on if it's a non-ag contaminant. So we would look at the suites like nitrate and chloride because those are just, known contaminants found in the groundwater, especially chloride because of all the de-icing chemical use. Other suites like the PFAS, we've been limited to what we can measure at the laboratories that we have under contract, because up until last year we could only monitor for 13 PFAS, and was just based on the laboratories methods that were available and also what we had on our state contract. And for the CECs, we've tried to align with the surface water monitoring that Mark Ferre, who is one of the co-hosts of this seminar series that he does in surface waters, because we wanted to stick with the same suite of chemicals. So if Mark finds CECA in the surface water, we can also have that same set of information for the groundwater, so we can let people know what the differences are in detection frequencies between the water types.
Okay, great. We have another question here from Mike. With infiltration of stormwater increasing, have you considered focusing some efforts to look at impacts from this?
Yeah, we've we have done a little bit of that back when there used to be a staff person who retired in our unit who was looking at monitoring in areas that were impacted by stormwater, and we've done a little bit of monitoring of special projects near, I believe it's a pervious pavement area in Shoreview, and we also work cooperatively with one of the water conservation districts to collect some groundwater samples near a large stormwater system in the Woodbury area. But that's, definitely something that would be good to monitor and something we should definitely think about within our group.
And then I had a question. Is there, what is the bromide ratio for potassium chloride fertilizer?
I'd have to look that up. I don't know that off the top of my head what other researchers have found for a chloride bromide ratio for the fertilizer. I know there's some other publications that were done by a researcher in Illinois that looked at a few different sources, but I don't know that off the top of my head.
Okay, yeah, I'm just curious because that U of M research came out that showed that fertilizer was almost equally a source of chloride as water softening,
Right.
which somewhat surprised me considering most of our water quality problems are in urban areas or downstream of a wastewater treatment facility. So I'm always looking for new information and data to help explain why we're not seeing a lot of chloride in our agricultural areas.
Yeah, one reason you may not is because that potassium chloride that would be applied to those lands would be over a much larger surface area compared to our state's urban areas and roadways. That may be why we're seeing lower concentrations in those areas. It just diluted out.
And I think that is it for questions on the chat. People can, of course, unmute at this point if they want to continue any questions or have any more conversations. But I just want to thank everyone for joining us and remind you that we will have another water issue seminar on June 11th. Daniel Dix will be joining us to talk about atmospheric component of EATR issues. Water issues. Thank you. So hopefully you guys can join us on June 11th. And we do record these, or at least if I remember to, I forgot to record Rebecca's last time. But we do record these and I save them in an X Drive folder. And I also post them on our Water Issues YouTube page. So we will share that link with you guys if you're interested. And you can find past recorded sessions there. And for like ones that I forget to record or we have technical difficulties, we do usually get the presentation slides from the presenter and have those available in the Water Issues X Drive folder as well. So please just contact myself or Mark or Liz if you guys want any more information. Ada wants to know, is it okay to share the presentation with outside parties? Yeah, especially the ones that we record and post on the YouTube. That's a public YouTube channel, so anyone has access to that site. So if we always ask permission from the presenters if it's okay to record and share that. So we have gotten permission from all of our speakers whose presentations have been recorded and posted on that YouTube site. All right. Well, I think that is it. Thank you so much, Sherry, for taking time and joining us today and sharing your work.
Yes.
And just a reminder, if anybody has other interesting water-related projects that they're working on or work that they're doing and you want to share it at an upcoming Water Issues Talks, we are always looking for presenters. So please let us know if you have an idea for a good future Water Issues Talk.